Hello and welcome to the MOOC on Applied Electromagnetics for Engineers. In this module we will discuss an important effect called standing wave on a transmission line and how to quantify that one using what we call as voltage standing wave ratio or simply standing wave ratio. We will see the importance of standing wave ratio and its relation to input impedance of a transmission line and reflection coefficient of a transmission line. Before doing that, let me just take couple of minutes to go back to that discussion that we had in the last module about lumped versus distributed. To refresh your memory, we talked of lumped regime when the time of flight was less than or equal to 0.4 Tr, and we talked of distributed when Tf was greater than or equal to 40 Tr. So, if I plot Tf versus Tr, you see that the slope of this line and any lines that is there in this region here in the lumped regime will be less than or equal to 0.4 Tr, and this is the lumped regime. So, the lines that are here will have a slope which is greater than or equal to 40 times Tr, and that would correspond to the distributed or the transmission line regime. This line not very well drawn, but this line has a slope of equal to 1, Tf equal to Tr. This is the gray area. Here you can apply both lumped regime as the transmission line theory. Both will give you reasonable accurate answers. Okay. With this, let us move on to study the standing wave ratio, which comes up in a very important aspect of power matching or the impedance matching, which we will take up later on during our study. Okay. What is the standing wave ratio? Let us first set up the problem. I have a transmission line over here which I will terminate with a load. Okay. This time the load could be any general load that I am considering. This load could also be frequency dependent because this could have some resistive as well as capacitive or inductive components to it. I have a voltage that is coming in, right. So, there will be a source kept at some distance. Okay. We will not specify where the source is kept. So, that is one of the things that I will talk to you about, how to set up these problems. So, all I am looking at is from the load side. So, this could for example be the situation when you are working with an antenna. Okay. You know that source is somewhere out there, okay, and your antenna is receiving the signals, or your antenna is connected and sending out signals onto the source, maybe the TV set which is kept in your home, far away from you, and you are working at the antenna side. So, what you are interested and what you are doing is to measure something at the antenna site, and you want to understand what is happening at the behavior. Okay. So, that is the problem that we are looking at. So, what we are looking at is I have a load here and it is connected to some source which is kept at a distance which we do not really know, but we do not really care also, and this the characteristic impedance of the transmission line is some Z0, and you have terminated the transmission line with some load impedance ZL. Clearly, if ZL is not equal to Z0, there will be some reflection. The voltage that is coming in after seeing ZL will be reflected partly. Similarly, the current that would be flowing in would also be reflected and constitutes a reflected current. So, there is a reflection coefficient associated with this one. But if I were to move along this transmission line and make my measurements, okay, of the voltage here, I will not just find what is V0 plus, I will actually find the forward going voltage as well as the backward travelling voltages. Similarly, if I make the current measurement, of course I do not do that, but if I were to hypothetically make the current measurement at any point on the transmission line, I would again see the forward going current I0 plus and the backward travelling current I0 minus. Okay. So, that is what it is, and what I am interested is to follow or try to find out the magnitude of this voltage as we move along the transmission line. This magnitude of the voltage along the transmission line will actually tell me the kind of load that we have connected. Supposing the load is unknown, which happens in most cases, if I want to find out the nature of the load, then I need to find out or track the magnitude of the voltage along the transmission line. How would that magnitude of the voltage change? It would change depending on the different types of load that I would terminate the transmission line with. So, I would like to get a slightly general expression and from there develop the concept of voltage standing wave ratio. I already know that if I take a uniform transmission line and terminate it with some load impedance ZL here and consider the location of the load to be at z equal to 0 and then move backwards towards the transmission line of some length. I do not really know what the length is, I do not even know where the source is terminated, but at any particular z on the transmission line, that is location on the transmission line, I know the total line voltage, okay, which will be a phasor which I can denote it as V bar of z, and this voltage will be the sum of the forward going voltage. I am considering the transmission line of no losses, that is the characteristic impedance Z0 is completely real, it is a lossless transmission line. So, the total voltage at any location z will be V0 plus e power minus j beta z. You do not individually measure this, you only measure the total voltage which would be given by V0 plus e power minus j beta z plus V0 minus e power j beta z. But V0 minus is related to V0 plus because I know what is, suppose I know what is the load. Of course, we will consider the cases where I do not know the load, but let us say because there is a load here and there is a characteristic impedance of the transmission line Z0, there will be a reflection coefficient at the load, may be unknown, but there will be certain reflection coefficient, okay, which we denote by gamma L. So, V0 minus, the amplitude of the reflected voltage is gamma L times V0 plus at the load, and you can make that substitution back into this one, okay. So, your total voltage V of z will be V0 plus e power minus j beta z plus gamma L V0 plus e to the power j beta z. If ZL is complex, that is it will have both resistive and reactive components, then if ZL is complex, then ZL and Z0, which could be real or it could be also complex, but in this case we are only considering real cases, the reflection coefficient gamma L will definitely be complex because ZL is complex. And just to refresh your memory, gamma L is nothing but ZL minus Z0 divided by ZL plus Z0, alright. So, this gamma L will also be complex. Any complex number can be represented or written in the polar form by giving its magnitude and the phase angle, which I will call this as phi L. So, I can substitute for gamma L into this expression and rewrite the magnitude of the voltage after taking the magnitude of the voltage on the right, on both sides, as V0 plus magnitude 1 plus mod gamma L e to the power j 2 beta z plus phi L, this entire thing magnitude, okay. So, let me denote the magnitude points by writing this with a red line, okay. I will leave this again as an exercise to you, it is a very simple exercise. Please find out and verify that the magnitude of the voltage that I have written is given by this. I can of course simplify because it is e to the power jx here, which I can simplify because e power jx is nothing but cos x plus j sin x. Simplify it, 1 plus mod gamma L is present here, it is multiplying cos 2 beta z plus phi L, and there is a imaginary component plus j sin 2 beta z plus bl, and after taking the magnitudes what you end up with is this expression. Again this is just one step verification. I will consider V0 plus to be real, therefore I removed the magnitude sign from that one, and in the bracket what I get is magnitude gamma L square plus 2 magnitude gamma L cos 2 beta z plus phi L. You can verify this, and there will be a 1 by half on top of it because this is a root of this entire expression, okay. Now, let us analyze this equation, okay. I have the transmission line at z equal to 0, I have connected the load, right. So, if I substitute z equal to 0, what do I get in this equation? So, at z equal to 0, that is at the location of the load, because my z axis is going here, all this transmission line is actually with z less than 0. That is to say, the numbers here, if you were to mark this one by a ruler, these numbers will all be negative, okay. So, that is the meaning of z less than 0 over there. So, at the load position, which happens to be right at z equal to 0, what is this expression tell me? The expression will tell me that magnitude of the voltage at the load location is given by V0 plus, here I have to put z equal to 0, which means 2 beta z is 0, so I get cos phi L. So, I get 1 plus magnitude of gamma L square plus 2 magnitude gamma L cos of phi L, whole to the power half. Of course, I need to know what kind of load I have terminated. Suppose my load happens to be open circuit. So, for an open circuited case, I know that gamma L is equal to +1, which also implies the magnitude of gamma L is 1 and the phase angle phi L will be equal to 0, 0 or 2 pi, does not matter. So, with phi L equal to 0, cos of phi L will be equal to 1, and what you get is 1 plus mod gamma L square plus 2 mod gamma L, which is nothing but 1 plus, because mod gamma L is 1. So, this would be 1 plus 1, 2, 2 plus 2 to the power half, which is square root of 4, which would be 2, and the magnitude will actually be equal to 2V0 plus. Okay. So, the magnitude of the voltage at the load will be 2V0 plus, which is what we know, because the entire voltage that is launched will be reflected. So, V0 plus and V0 minus will be exactly equal to V0 plus, and at the load point they will add together and they will be, they will give you magnitude of 2V0 plus. Suppose I consider the load to be short circuit. For the short circuit, I know that gamma L will be equal to -1. You go back to the expression and find this out. The magnitude of gamma L will still be equal to 1, but this time the angle phi L is equal to pi. So, you go back to this expression and write this. So, you get 2 minus 2, which would be 0, and the magnitude of the voltage here will be equal to 0. This is true, but this is also true only at the load location, because that is precisely at which point we are evaluating my voltage magnitude using this expression. Okay. As you move away, this expression predicts that the voltage magnitude will change. Okay. But there is a certain point where the voltage magnitude will become maximum. When will that happen? If you look at the equation closely, as z changes, 2 beta z also changes, and the total argument of the cosine function, which is 2 beta z plus phi L, must go through some integer multiple of 2 pi at some point. When it goes through the integer multiple of 2 pi, I see that the magnitude of the voltage would have become maximum. Similarly, when it goes through a multiple of when will the cosine function go through its minima? When it goes through an odd multiple, right. So, when it goes through an odd multiple, the argument of the cosine function, then the sign of cos becomes negative and the voltage would actually be minimum. So, the maxima are attained, or we say that voltage maxima occurs at locations when 2 beta z plus let us call this as z max, okay, 2 beta z max at the location z equal to z max plus phi L happens to be some integer multiple of 2 pi, and please note that you have to choose the value of n such that z max is negative. Because of the notational convention that we have used, the transmission line is described by the values of z, which is negative, because the load is sitting at z equal to 0. Okay. When will we have minima? Minima occurs when 2 beta z min, I will just want to denote the differences between max and min. So, this must be equal to 2n plus 1 into pi. Again you have to choose in such a way that z min is also negative. Okay. Both z max and z min must be negative. What is the maximum value of this voltage, or at what is the value of the voltage maxima? The value of the voltage maxima happens to be 1 plus mod gamma L into V0 plus. One short verification, please verify this one. Okay. Similarly, verify that the minimum voltage will be V0 plus into 1 minus mod gamma L. Please note that magnitude of gamma L depends on load type that you have connected. Again, you can verify this, that these two expressions are okay. Now, we define a quantity called as voltage standing wave ratio. Okay. We call this voltage standing wave ratio, and we either write this as VSWR or simply SWR, with the meaning that it is the voltage that we are considering. Okay. The current standing wave ratio will be dealt with an exercise, and that value will just be minus of VSWR. Okay. So, this voltage standing wave ratio, as you might have guessed, is the ratio of the maximum voltage to the minimum voltage that can occur along the transmission line. Please note that both maxima and minima occur at different positions. Okay. they both do not occur at the same position. So, this position will not have both Vmax and Vmin unless we are considering a very special case to which we will come. Okay. So, usually Vmax occurs here and then Vmin occurs, again Vmax occurs, again Vmin occurs. This is a periodic way in which it changes for a lossless transmission line. Okay. And we will also calculate what is the distance between a voltage maxima and a voltage minima shortly. So, this standing wave ratio or VSWR, sometimes denoted by S, is given by the ratio of the maximum voltage to minimum voltage. From the expressions you can easily substitute and then show that this is given by 1 plus mod gamma L by 1 minus mod gamma L. Okay. What is the range of S? Well, gamma L can go anywhere from 0 to 1, right. So, 0 corresponds to no reflections, 1 corresponds to full reflection. Therefore, S correspondingly must go from 1, right, to infinity. So, S must be equal to 1 when gamma L equal to 0. So, clearly this would be equal to 1. When gamma L is equal to 0, S will be equal to 1. When gamma L is equal to 1 for a open circuit or a short circuit or for a reactive termination, then S will be equal to infinity. So, this is the range over which S can vary, this is the range over which reflection coefficient can vary. These are all for the passive lossless transmission lines. There are no active amplifiers in the line that we have considered. What is the importance of standing wave ratio? It turns out that you can't actually measure the reflection voltage or reflection coefficient so easily, because we will see why in a later class, but what is reasonably okay to measure is the voltage maxima, okay, and the voltage minima. This is a classic experiment to actually determine the type of load. You might perform these experiments in your microwave laboratory. Okay. You take your transmission line, you do not know what is the load, we will talk about the proper measurement later on, but you have a load here, and what you do is you connect a voltmeter or rather a power meter, and then you keep moving this along the length of the transmission line and record the voltage magnitude that you are going to see, not the phase but only the voltage magnitude. So, you record this voltage magnitude. At some point you reach a max, keep going, you will reach a minimum. Okay. When you take the ratio of maximum to minimum, you will be able to find out the magnitude of the reflection coefficient. Okay. Also, by noting where the maxima and the minima occurs on the transmission line, you will be able to find out the phase of the reflection coefficient. So, you would have found out the magnitude, you would have found out the phase. Knowing the value of Z0 and the value of full reflection coefficient gamma L, you will be able to calculate the value of the unknown load impedance. So, this is in fact the importance of voltage standing wave ratio. You can make these measurements and determine the unknown unknown voltage, unknown load that you have terminated the transmission line. Another important application or another important thing that occurs with standing wave ratio is that this is the quantity that is specified by most RF device manufacturers. Okay. When SWR, if the devices are well matched, we will talk of matching later on, if the devices are well matched, then this SWR will be about 1, okay, that is the ideal value. Anywhere from 1 to 1.25, 1.5 is also okay, but if this standing wave ratio happens to be larger, say by 3 or 4 or 5 or maybe 10, then we know that the two systems are not very well matched and there is considerable reflection occurring between the two components, leading to lot of problems. First, your power efficiency goes down, because the voltage is circulating and trapped, the wire will also have to be able to withstand this higher voltage. So, all these problems can occur. To put it simply, standing wave ratio is a quantity that is measurable and will give you lot of insight about the type of the load that you have connected as well as what is happening on the transmission line or in terms of the matching between two components. Okay. We will go back to a few special cases so that this concept is clear to you. Consider what happens in the case when gamma L is equal to 0. Okay. When can I have this situation? When I terminate the transmission line with its own characteristic impedance Z0. In this case, since gamma L is equal to 0, the standing wave ratio is equal to 1. What does it mean? It simply means that if you go back to the expression of the magnitude of the line voltage, this turns out to be equal to V0 plus, magnitude of V0 plus. What it means is that on the transmission line there is only propagating voltage and there are no back reflected voltages. So, when there are no back reflected voltages, your voltage phasor would simply be equal to V0 plus e power minus j beta z. Okay, this is the only wave that is propagating, there are no reflections, gamma L equal to 0, and the magnitude of this will simply be equal to V0 plus. So, in this case the maximum voltage will be equal to minimum voltage, and this location of maximum voltage and minimum voltage occurs at all points on the transmission line. So, this is only a very special case when S is equal to 1. Consider the case when gamma L magnitude is equal to plus 1, okay, and the phase angle phi L equal to 0. In any case, the standing wave ratio SWR in this case, or S as we can denote, will then be equal to infinity, because gamma L magnitude is equal to 1. Okay. We can have this situation either by an open circuit or the short circuit. For open circuit the phase angle is 0, for short circuit the phase angle will be equal to pi. But if I find out what is the magnitude of the voltage V of Z, you will see that this would be given by V0 plus 1 plus magnitude gamma L square plus 2 magnitude gamma L cos 2 beta Z plus phi L, correct, to the power 1/2. In this case gamma L magnitude can be equal to 1. So, I can replace them with 1 here, and I can replace this one also by 2. So, this would be 1 plus 1, which would be equal to 2. Okay. So, this would be 2 plus 2 cos 2 beta Z plus phi L. Clearly phi L will be equal to 0 for the open circuit case, and this is how you are able to find out what is the voltage. Where will the maxima occur here? When 2 beta Z is equal to 2 pi, or rather 2 n pi, n must be chosen such that Z will be negative. So, I can't choose n equal to 0, I can choose n is equal to minus 1. So, when I choose n equal to minus 1, I get 2 beta Z, I am finding the maximum, this would be equal to minus 2 pi. Since beta is 2 pi by lambda, the maximum occurs here. If I expand beta to 2 pi by lambda, and maxima occurs here at minus 2 pi. So, 2 pi cancels on both sides, and maxima occurs at lambda by 2, minus lambda by 2, which means that from the load, okay, so this is the open circuited transmission line, from the load at a distance of lambda by 2, I get a maximum. Of course, in this case there is one maximum right on the load itself. So, I forgot about that one. So, of course, in this case there is one maximum right on the load. What it means is that there will be a voltage maxima through a minima and one more maxima, and the distance between the two maxima happen to be lambda by 2. Clearly, the distance between maxima and minima will be lambda by 4, as you can easily verify. What about the short circuit case? In the short circuited transmission line, first there will be a voltage minima, then there will be a voltage maxima at a distance of lambda by 4 from the load. Okay, so, this is the load location. Again there will be one minima at lambda by 2 away from the load. Okay. As before, maxima and minima are separated by lambda by 4 with respect to both. Okay. Now, I consider a very special case of pure reactance termination. Suppose I consider the case where ZL is either an inductor or a capacitor. Suppose this is an inductor with plus jz0. Okay. So, this is an inductor. You can clearly see that the magnitude of the reflection coefficient will be equal to 1, which indicates that SWR must be equal to infinity. Why will this happen? Because Vmax could be some finite value, but Vmin on a transmission line which is lossless, and in this case will be equal to 0. So, because Vmin is equal to 0, the ratio of finite value to 0 will go up to infinity. Okay. So, that is about the magnitude. But what about the phase angle? The phase angle here phi L will be equal to pi by 2. So, where will the location of maxima be? So, look at this equation again, 2 beta Z max plus pi by 2 must be equal to sum 2n into pi. Suppose I consider n is equal to 0, which is a valid situation in this case. So, in that case what will happen? 2 into 2 pi by lambda into Z max will be equal to minus pi by 2. So, pi cancels on both sides, and Z max occurs at minus lambda divided by, there is a 2 here in the denominator, there is a 4 in the numerator. So, that would be 8, right. So, the maximum occurs when this one is equal to minus lambda by 8. Okay. You can also write down what is lambda. Lambda is nothing but up divided by frequency. So, the location of the maxima is given by minus up divided by 8 into f. Okay. This is the location of the first maxima away from the load, okay, away from load for the case of a termination which is a pure inductive termination. Okay. So, this pure inductance had the load value equal to plus jz0. I will leave this as an exercise for you to find out when will the, for the case of a termination with a pure capacitance, that is when ZL is equal to minus jz0, where will the first maxima be located. It turns out that the first maxima will be located at a distance of lambda by 4 from the previously calculated value. So, in that way the inductance and capacitances, they will shift the maxima voltages and the minima voltage values by about lambda by 4. These concepts are important because in general, of course, you will not, I mean you will have to find out the maxima and minima locations based on an experimental value and from then back calculate what is the load. But in a in a question where we give you what is the load value, then it is easier for you to find out where the maxima and the minima are located. Okay. Moreover, these values that we have found are quite okay for simple cases, but when you consider a general case where the load happens to be something like RL plus JXL, then it will be very difficult for you to keep doing this algebraic manipulation. So, there is a graphical way in which you can solve these problems. This graphical way involves the use of what is called as a Smith chart, which is what we are going to discuss in the next class. Okay. So, until then, please revise your concepts of load termination, standing wave ratio, reflection coefficient and the relationship between all these impedances, reflection coefficient and standing wave ratio. Thank you very much.